Limits are fundamental to calculus. They provide a way to describe the behavior of functions as their inputs approach specific values. Imagine a cheetah closing in on its prey. The cheetah gets closer and closer, but doesn't quite reach its target until the final leap. Limits help us analyze this approaching behavior in mathematics. Think about a car accelerating along a racetrack. We can use limits to determine the car's instantaneous speed at any given moment. This is because limits allow us to analyze the car's average speed over increasingly smaller time intervals, approaching an infinitesimally small duration. Limits are essential for understanding concepts like continuity, derivatives, and integrals, which form the backbone of calculus. They enable us to analyze functions and their behavior in a precise and rigorous manner. By mastering limits, we unlock the power of calculus and its ability to model and solve complex problems in various fields, from physics and engineering to economics and biology. In calculus, we often talk about functions approaching certain values. This concept of approaching is at the heart of limits. A limit describes how a function behaves as its input gets arbitrarily close to a particular value, without necessarily reaching that exact value. Consider a function with a hole in its graph. The function might not be defined at the point where the hole exists. However, using limits, we can still describe how the function behaves as its input gets closer and closer to that point, even though the function's value is undefined there. Imagine walking towards a wall. You can get closer and closer to the wall with each step. However, you never truly reach the wall because you always take another step. Limits work similarly. We examine the function's behavior as the input gets infinitesimally close to a specific value, even if it never reaches that exact value. This concept of approaching but not necessarily reaching is what sets limits apart from simply evaluating a function at a point. Limits provide a way to describe the function's behavior in the neighborhood of a point, regardless of whether the function is defined at that point. Mathematicians use a specific notation to represent limits. Understanding this notation is crucial for working with limits effectively. The standard notation for a limit is
lim x der fx =lay.
Let's break down what each part of this notation means.
This stands for limit and indicates that we're looking at the limiting behavior of a function. This means that the variable x is approaching the value a. It signifies that we are interested in the function's behavior as x gets closer and closer to a. This represents the function we are analyzing. It could be any mathematical expression that defines the relationship between the input x and the output fx. This is the limit of the function as x approaches a. It represents the value that e at x approaches as hx gets arbitrarily close to a.
In essence, this notation tells us that as x gets closer and closer to a, the value of the function fx gets closer and closer to L. Determining the limit of a function can be done in several ways: graphically, numerically, and algebraically. Each method offers a different perspective on how a function behaves near a particular point.
We can visualize a function's limit by plotting its graph. By examining the graph, we can see what value the function approaches as the input approaches the target value. This method is intuitive, but can be less precise, especially for complex functions. This method involves creating a table of values for the function as the input gets closer and closer to the target value. By observing the output values in the table, we can get an idea of what value the function approaches. However, this method is also limited by the number of values we can calculate. This is the most precise method for determining limits. It involves manipulating the function algebraically to simplify it, and then substituting the target value into the simplified expression. This method provides an exact value for the limit, if it exists.
Each method has its strengths and limitations, and the best approach often depends on the specific function and the desired level of precision. Section 5. One-sided limits and their significance.
Sometimes, we're interested in how a function behaves as its input approaches a specific value from a particular direction.
This is where one-sided limits come into play. They allow us to analyze the function's behavior as the input approaches the target value from either the left or the right side.
A left-hand limit describes how the function behaves as the input approaches the target value from values smaller than the target value. It's denoted by adding a minus superscript to the target value in the limit notation.
A right-hand limit describes how the function behaves as the input approaches the target value from values larger than the target value. It's denoted by adding a plus superscript to the target value in the limit notation.
For a limit to exist, both the left-hand and right-hand limits must exist and be equal. If either one-sided limit doesn't exist, or if they exist but are different, then the overall limit does not exist.
Section 6. Continuity as seamless flow.
Continuity is a fundamental concept in calculus that describes functions whose graphs have no breaks, jumps, or holes. A function is considered continuous at a point if its graph has no interruptions at that point.
For a function to be continuous at a point, 3 conditions must be met. First, the function must be defined at that point. This means the function has a value at that particular input.
Second, the limit of the function must exist at that point. This means the function approaches a specific value as the input approaches the target point.
And third, the limit of the function at that point must be equal to the function's value at that point. This ensures that there are no abrupt jumps or holes in the graph.
If any of these conditions are not met, the function is said to be discontinuous at that point. Discontinuities can occur in various forms, such as holes, jumps, or asymptotic behavior.
Section 7. Properties of limits, essential tools.
Working with limits often involves manipulating expressions and applying specific properties to simplify calculations. These properties provide a set of rules for working with limits, making it easier to evaluate complex expressions.
Some essential properties of limits include the constant multiple rule, sum difference rule, product rule, and quotient rule.
The constant multiple rule states that the limit of a constant multiplied by a function is equal to the constant multiplied by the limit of the function.
The sum or difference rule states that the limit of the sum or difference of 2 functions is equal to the sum or difference of their individual limits.
The product rule tells us that the limit of the product of 2 functions is equal to the product of their individual limits.
And the quotient rule states that the limit of the quotient of 2 functions is equal to the quotient of their individual limits, provided the limit of the denominator is not 0.
These properties are instrumental in simplifying limit calculations and are often used in conjunction with algebraic manipulation to determine the limit of a function.
Section 8. Calculating limits algebraically, a step-by-step guide.
Calculating limits algebraically involves manipulating the function to simplify it and then substituting the target value into the simplified expression. This method provides an exact value for the limit if it exists.
First, try direct substitution. If the function is defined at that point and the result is a real number, then that's the limit.
If direct substitution results in an indeterminate form, like 0 over 0 or infinity over infinity, we need to simplify the function algebraically. This might involve factoring, rationalizing, or using trigonometric identities.
After simplifying the function, try substituting the target value again. If the result is a real number, then that's the limit.
If simplification doesn't resolve the indeterminate form, we can use L'Hopital's rule. This rule states that the limit of the quotient of 2 functions that both approach 0 or both approach infinity is equal to the limit of the quotient of their derivatives.
By following these steps, we can calculate the limit of various functions algebraically.
Section 9. Applications of limits, the foundation of calculus.
Limits are not just a theoretical concept, they form the foundation for many crucial concepts in calculus and have numerous applications in various fields.
Derivatives, which represent the instantaneous rate of change of a function, are defined using limits. The derivative of a function is the limit of the difference quotient as the difference in input approaches 0.
Integrals, which represent the area under a curve, are also defined using limits. The definite integral of a function over an interval is the limit of a Riemann sum, which approximates the area under the curve using rectangles.
Limits are also essential in determining whether an infinite series converges or diverges. Various tests for series convergence, such as the ratio test and the root test, rely on limits to analyze the behavior of the series terms.
Beyond calculus, limits find applications in physics, calculating instantaneous velocity and acceleration, economics, analyzing marginal cost and revenue, and computer science, approximating values and optimizing algorithms.
In essence, limits are a fundamental tool for understanding and analyzing change and continuity in various contexts. They allow us to explore the behavior of functions and systems in a precise and rigorous manner, making them an indispensable tool in mathematics and beyond.